All right, very good. So uh, the title of this talk is Knots, Virtual Knots, and Virtual Knot Cobordism. It's meant to be elementary and introductory, so please ask questions if you wish about anything that comes up. Let me see. Yeah. All right. So I remind you that we can do diagrammatic knot theory using Reidemeister moves. Um, and I'm sure everyone here has seen these, so I won't go into saying much more about that. But for virtual knots, we're going to be studying knots not just in the three-dimensional space, but also in surfaces crossed with the unit interval. Regular knot theory can be thought of as diagrams in a plane or diagrams on the two-sphere, and that's the same as talking about knots in a thickened two-sphere, in a two-sphere across the unit interval. And similarly, if I was going to think about, for example, knots on the surface of a torus, knots in a thickened torus, then I can draw diagrams on the surface of a torus as I have in the middle of this slide. And that would be a sufficient way to think about diagrams for knots in a thickened surface, to draw diagrams on the surface. But we're going to take one further step and abstract the diagram from the surface, um, essentially by means of the kind of projection that you see on this slide, where I have a knot on the surface of a torus, a diagram on the surface of a torus, and I have projected it into the plane. And in so projecting it, I have to remind myself that some of the crossings in the projection are different from the others. Two of the crossings in this projection are weavings on the surface, but one of them has to do with the fact that the knot went around the handle and so is going underneath itself, but that's not a crossing. And so that will be designated by a little circle around that crossing and called a virtual crossing. We can make it systematic how to get between knots that are drawn as virtual diagrams like this and knots in some surface by performing the construction that you see on the left, where I take a ribbon neighborhood of the virtual diagram, and ribbon neighborhoods are produced by forming the obvious sort of ribbon neighborhood of a crossing, where I include a little disk that has the crossing and some bits of ribbon that can be attached along the lines outward from that crossing. And at a virtual crossing, I take two strips that are independent of one another, one for each of the lines that crosses. Of course, when I make a drawing of this, I have a tendency to draw one of those strips over the other, but that's an artifact of drawing as though it were in three dimensions, when in fact the surface that I produce is meant to be an abstract-oriented surface. In any case, let's call that the ribbon graph of the virtual diagram, or the abstract link diagram of the virtual diagram, as it was called by Kamadas when it was originally invented as a way to as a way to think about knots on a surface. And if you take that ribbon graph and add disks to its boundary, then you get a surface with the least amount of genus for that diagram that will hold that knot diagram. And in this case, if you added disks to the boundary of the ribbon graph on the left, you would find that you had produced the embedding in the torus that I showed you before. This is certainly more systematic than trying to talk about projections. And one can go in the other direction as well. Whoops. If one had a diagram in a surface, one can form the same ribbon graph neighborhood construction in the surface and then excise, cut out the ribbon graph. And once you've cut out the ribbon graph, keeping it quite literally as I have here, it may have some twisting in it. in the way you work, because you're working in something visualized in 3 dimensions. And that twisting is then eliminated, flattened, so you draw it in a flattened way and take the corresponding projection in the plane. So you see that we can go back and forth between knots in surfaces and virtual diagrams in this way. But on the other hand, and I think I have a slide that illustrates it, so let me see if I can find that slide. Just go forward till I find it. Um, sorry, I shouldn't have bothered you. Um, let's go forward 2 slides to this one. Um, in this case, um, this is a good illustration of another way to think about it. If I have a diagram, I could, if I like, take each virtual crossing and make it into a little handle. But the point that I'm making now is this, and I ask you to imagine it rather than look for the nice slide that I had drawn and mislaid. As suppose that you look at this knot on the torus and imagine that it's drawn on a double torus, but it isn't having anything to do with the other handle in the double torus. Then when you did this construction, it wouldn't know about the other handle because it takes the ribbon graph that's hugging the diagram. So you see the result of taking the ribbon neighborhood, cutting that out, and then adding disks or adding other handles to it is that handles outside the ribbon neighborhood are ignored. And so it turns out that by thinking it through that way, the virtual diagrams taken up to the equivalence relation I'm about to show you are equivalent to knots in surfaces up to cutting out the extra handles or putting them in. So you can do surgeries on the surfaces to remove their extra handles as long as the cutting out or putting in of extra handles doesn't disturb the diagram. And the theory that we are looking at now becomes the theory of knots in surfaces taken up to surgeries on them that would remove or add extra handles that do not disturb the embedding of the knot. But we're going to make it into a diagrammatic theory. And the other thing about the diagram is that it has a Gauss code. So it's worth remarking on the Gauss code right now. Here over on the right in this figure is this same diagram, but now I've labeled its real crossings, and we can walk along them, and then we go 1, 2, and then come back to 1, and then 2. So the bare Gauss code is 1, 2, 1, 2. And the full Gauss code, keeping track of orientations and everything, is over 1 at a positive crossing, under 2 at a positive crossing, and under 1 and over 2. But you see, that code is not the code for something that could be drawn in the plane. If you tried to draw it in the plane, you would find that you had to have the virtual crossing. So another way of thinking about the virtual knot diagrams is that they have Gauss codes, and the Gauss codes are not necessarily planar. Now, another point that I want to make about the ribbon surface, the ribbon graph, the abstract link diagram, is that once you've made it, you might be curious as to what genus surface did I fit that virtual diagram into. And there's a nice way to think about that. So we're going to add disks, remember. So if you ask yourself, well, what would the genus of the surface be? You have a graph in that surface that you have created. The vertices of that graph are the classical crossings in the original diagram. The edges in that graph are the number of edges in the original diagram, where I do not count a virtual crossing when I'm looking at an edge. So in this case, you see 2 vertices, and the number of edges is equal to is obtained in terms of the number of vertices, as a matter of fact, because 4 times the number of vertices is going to be twice the number of edges, because you're counting at every vertex 4, and you're going to count every edge twice. So that says vertices is equal to edges over 2. Um, and and then you have Euler's formula, which says that vertices minus edges plus faces is equal to 2 minus 2g, where g is the genus of the surface. But the number of faces is the number of disks you added. And the number of disks you added is the number of components in the boundary of the ribbon graph. That I called L here. And if you look at this one, you see that it has 2 boundary components, one long one that goes all over the place and one tiny one up there in the top of the diagram. So that tells us that in this case we have genus 1. And in general, we have, by doing a little calculation with that the genus is equal to 1 plus the difference between the number of crossings in the diagram and the number of loops in the boundary divided by 2. 1 plus v minus L over 2. So this is a useful formula to make note of, because when you do examples, one of the first things you often think about is, well, what genus surface am I going to get from this knot? And of course you would like the least genus surface among all of the different representatives for that knot, but that's harder. And as I said, another way to get to a surface is to think of drawing a handle that lets the virtual crossing detour. This does not always give you the least genus surface, but it is a way to, in a well-defined way, to go up to a surface that corresponds to your virtual knot. And now for the moves. Here is the extension of the Reidemeister moves to allow you to do virtual knot theory. It's the usual Reidemeister moves on the left, and then these moves that you see on the right for virtual crossings. And if you're thinking in terms of the ribbon graph, then you realize that all of the moves in the big box are certainly allowed, because you just have bits of ribbon going over and back over each other, and it doesn't matter whether they're over or under. And similarly for the last move on the bottom, where a ribbon is going above a crossing, but that ribbon can be transposed. So these moves are all true for our model. And it is in fact the case that we can take as a diagrammatic theory this version of extending the Reidemeister moves, and then the virtual diagrams that you use correspond to knots on surfaces taken up to handle stabilization, as I described before. All of the virtual moves that you saw on the right can be summarized by saying that they are detours. That is, if you have a consecutive collection of virtual crossings, you can cut them out and reroute it somewhere else. So it's easy to remember what the virtual moves are. They're all detours. Look back at the moves on the right over here, and you'll see that. Every one of them can be redescribed as, I cut out 2 consecutive virtual crossings in the case of the 2 move and redrew it without any virtual crossings. I cut out 2 consecutive virtual crossings in the case of the 3 move, and I put it down there below that other crossing. And similarly for the mixed move. All right, so we have a diagrammatic theory like that. And you might think that these moves, which I've illustrated on this slide, would be natural diagrammatic moves, but we forbid them. They're not part of this system. You can add one of them if you wish, and you get a new theory. For example, if you add F1, you get what we call welded knot theory, after the work on braids by Rourke, Fenn, and Rimiani in the 1990s. And their work on braids becomes a work on knots, and those are called welded knots. And welded knots are very interesting to study. Welded knots from this point of view are virtual knots, and you allow the first forbidden move. If you allow both forbidden moves, then Sam Nelson and the Kamadas proved that you could unknot anybody. So you don't want to add them both. But you could add F2 instead of F1, and you'd get another version of welded knot theory. We're going to talk about the bracket polynomial. It's possible you already are familiar with the bracket polynomial. This works for classical knot theory and for virtual knot theory, and gives an invariant of knots, which is of interest to us quite a bit. And the notion behind the bracket polynomial is that you would take a crossing and you would smooth it in the two possible ways that are indicated here, and form a polynomial by adding up in a skein relation like this. You just expand for each crossing, and eventually you would get collections of circles. And the circles will be evaluated in a certain way that we'll see in a moment. So I want to go through the basics of the bracket polynomial so that we can use it. So the first thing is to realize that we can define it in the following way. We're going to form states which consist of smoothing at every crossing by some choice of smoothing. And I have the convention that if I labeled my crossing as it is labeled in this slide, A's and B's, then if you take the smoothing that brings the two A's together, I call it the A smoothing. And if you take the smoothing that brings the two B's together, I call it the B smoothing. And then you can choose A and B smoothings at every crossing and form states. The state I've illustrated here has all A smoothings. And then I count the number of loops in the state, and I call that norm S. And I count the product of the A's and the B's, and I call that KS. And then you can form the summation of KS times D to the norm of S. That's the products of the A's and the B's multiplied by D, another variable, raised to the number of loops. This is the unnormalized three-variable bracket polynomial. And it satisfies the skein relation that we saw before for the following reason, that at any point in the diagram, the states will be either of type A or type B. So if you divided the states into those that are A at a given crossing and those that are B at a given crossing, then you have a disjoint union of two collections of states, and the summation is the summation over the first collection plus the summation over the second collection. The first collection contributes an A, and then it looks like the states of the diagram with the smoothing. And the second contributes a B, and it looks like the states for the diagram with that smoothing. And that's the proof of the skein relation that we had. Of course, the definition I just gave you is well defined. We have simply said it's a sum over these particular combinatorial things, each of which is well defined. And then we can examine how it behaves under the Reidemeister moves. And for that purpose, I have shown you in this slide how it behaves under the second Reidemeister move up at the top. The second Reidemeister move, I used the skein relation and expanded it. And as you see, I get four terms because there are two crossings. And they go AB, A squared, B squared, and AB, as you see, and collect the terms with a loop giving us a D, and we get AB times the bracket on the vertical parallel smoothing, and ABD plus A squared plus B squared times the horizontal smoothing, where I'm using vertical and horizontal just to describe the picture. And then what do we need in order to get invariance then? Well, one way to get it is simply to say that AB will be equal to 1, and that ABD plus A squared plus B squared will be equal to 0, to collapse the algebra in that way. If you do so, then B is A inverse, and the D will have to be minus A squared minus A to the minus 2. And if you do that, it will be invariant under the second Reidemeister move. Having chosen that, we look at the third Reidemeister move and expand on a crossing as I indicate here, the one at the bottom, and you see that the right-hand piece is very simple. The left-hand piece has a Reidemeister 2 move that you could do, but you've already adjusted it to be invariant under the Reidemeister 2 move. So you slide it down into the middle, and then you slide it down a little farther, and you see, oh, that expansion is the expansion for the crossing above rather than below. I see I made a mistake in drawing my slide. The crossing at the bottom got switched accidentally. It is, as you see, correct that it gives me the other switch of that crossing when you put it back together. And so you get the third Reidemeister move. Sorry for the misprint on that slide. Then we use +1 and -1 as indicated for the signs of crossings. That's a right-hand rule choice that you probably already use. And that means that a little curl, like the one I've illustrated at the top of the slide, would be a plus curl no matter how I oriented it. And a plus curl turns out to get an AD plus B when you do the calculation, and that turns into a minus A cubed. And a minus curl gives you a minus A to the minus 3. So those are the details of the invariants. Simple enough. And the states in general, well, they look like this. You smooth, and eventually you get all of the different states. You can think of it as coming from the Skene relation or having been produced by some nice method, and you get them all, and the polynomial is the sum of the contributions of each of those states. A very good and important way to reorganize the states is Khovanov's way, which is related to Khovanov homology, which we'll talk about in the second talk. This is called the Khovanov complex, but at the moment it's just the organization of the states. I have put the all A state of the trefoil over on the left, and then an arrow going from one state to another changes exactly one site from an A to a B. So as you see, the three arrows going out of the all A state on the left change one place to a B of the three places that are available. And then the arrows going out from them change one of the A's to a B, so that the second column has one B, the third column has two B's, and the fourth column has all B's. And you can systematically generate all the states from the all A state by drawing such a picture. And then you see that the states themselves are lying on the vertices of a hypercube. In this case, since there are three crossings, it's an ordinary cube. But if there were four crossings, it would be a four-dimensional cube. And if there were five crossings, it would be a five-dimensional cube. And in general, a hypercube catalogs its vertices, catalog the states. And from the Khovanov point of view, this is a category. That is, it generates a category. Arrows from object to object, and if you wanted to make it into a category, you can say to yourself, well, the objects are these state diagrams. These arrows are the generating arrows for the category. So I could, to make a category, start at the left one and go by the arrow up, and then go by an arrow down, and then go by an arrow over to the right, and I've composed some arrows, and I have a morphism from a diagram over on the left to some other diagram over on the right. You can compose arrows, and then you form a category. And of course, that means that implicitly every object has an identity arrow. So given a directed graph, you can always make a category. But now comes the question, which turns out to be significant, that Khovanov asked. Couldn't we use the category to get at invariance of the knot? Couldn't we somehow understand how this collection of states as a category moves around when you do Reidemeister moves on the knot? And from that, couldn't we understand better than just a polynomial, as we have already defined, what is the nature of the invariance that comes from these states? And what Khovanov discovered is that indeed there is a way to measure the category and to form a homology theory that is deeper than the Jones polynomial or the bracket that we have described so far. And we'll talk about that more. But for now, I just pointed out to you as a very convenient way to think about the structure of the states. Now, to get full invariance of the bracket, you need to multiply by what happens to the loop. And so we need a quantity which is not quite invariant, and that is the sum of the crossing signs of the knot. So here I have drawn a trefoil knot on the blackboard, and it has all positive signs, and its ride is 3. The ride is the sum of the crossing signs of the knot. And then we can normalize the bracket by taking minus a cubed, which is the value of a plus loop, raised to the minus ride, and that compensates for the ride change of the bracket and gives us something that's invariant. Also, when I write sharp bracket, I mean that the value of a single loop is equal to 1. It is 1 over d times the bracket that we already defined. So now we have a fully invariant polynomial, Laurent polynomial, invariant under all 3 Reidemeister moves. And it's that one that turns out to be equivalent to the original Jones polynomial, although in this slideshow, I don't think I'm telling you the formulas about that. But here's how it looks on the blackboard. And a good theorem about it. The theorem is that if you take the mirror image of a knot, so here's the trefoil knot, and here's its mirror image. And the mirror image I'm thinking of is to switch all the crossings. So you see that trefoil knot, and then you flip every crossing in the knot, and you get K star. Well, if you have the mirror image of a knot, then if you calculate the bracket of the mirror image, you see that it interchanges A and A inverse. Remember, A inverse is the B. They get interchanged. And same for the normalization. They get interchanged. So that means that the value for the mirror image is the value for the knot with A inverse replacing A. And if it should happen that that doesn't give you an equal, if it should happen that that gives you a different polynomial, if it should happen that fk star is not equal to fk of A, well then you know that the knot couldn't be equal to its mirror image because they would have different invariants. So here's the short calculation in the case of the trefoil. I want to calculate the bracket of the trefoil. So I begin by smoothing 2 crossings. In the blackboard, you see it. And then I get a hopflink on the left and a little curly guy on the right. And I smooth 1 crossing more on the hopflink, and I get 2 curly guys. And so I don't have to look at all 8 states. I only look at three partial states, each of which is made up of curls, because I know what happens under curls. And so the bracket polynomial of the trefoil is the sum of evaluations of 3 little curly diagrams that you see there. The left one, it has 2 a's, so it's a squared, and it's got 1 little curl, which gives you a minus a cubed. The one in the middle on the bottom has just an a and an a inverse, and they cancel. That's the 1, and it's got 1 little curl, and that gives you a minus a to the minus 3. I let you look at it yourself carefully to check which curls are positive and which ones are negative. And the last one has 1 smoothing, only 1, and it gives an A inverse, and 2 curls, and you get a minus a to the minus 3 squared. Adding all that up, we get minus a to the 5th, minus a to the minus 3, plus a to the minus 7 for the raw bracket of the trefoil knot. And then we multiply by minus a cubed to the negative ride, and that's 3, and we get minus a to the we get a to the minus 4 plus a to the minus 12 minus a to the minus 16. There is the fully invariant polynomial for the trefoil knot. And you see that if you change A to A inverse, the polynomial changes radically. And therefore, the trefoil knot and its mirror image are inequivalent. So this is a simple proof that the trefoil knot and its mirror image are not the same. Simple proofs of this kind do not come easily. Another way to do it that is not too complicated but uses a lot more geometry is the way of Ken Perko, who uses some branched covering spaces to verify this. Other ways to do it involve a little more mathematics. For example, the signature of a knot can be defined, and you can use the signature to prove that the trefoil and its mirror image are distinct. But this is very interesting that the Jones polynomial can detect knots from their mirror images. And we do not know fully when this works. There are knots that the bracket polynomial will not distinguish from their mirror images that are nevertheless distinct from their mirror images. And we do not know the extent to which this idea, this method, does detect mirror images when we're working with the bracket polynomial. Now back to virtual knots. Here's an interesting virtual knot, just to illustrate Gauss codes and other things. As you see, it's got three real crossings and a couple of virtual crossings. And if you look at its Gauss code, bare Gauss code, it's 1, 2, 3, 1, 2, 3, just like the trefoil. But you'll find that if you want to write it in the plane in an oriented way, keeping all the signs and everything, that it won't fit in the plane without the virtual crossings. This knot, in fact, has a unit Jones polynomial, and we'll see that in a minute or two. Now, there are variations on virtual knot theory, and I wanted to mention that. One of the variations is welded knots, which, as I said, is you take the first forbidden move plus the other. And this welded knot plus virtual knot theory, and this turns out to be related to the braiding of circles in 3 space, and to 4-dimensional tubular braids, and to embeddings of tori in R4. And in the interest of time, I won't talk about that right now, but if we had a little time in the next talk, I might come back and show you a thing or two about that. It's a very interesting theory. Another theory that I like is what I call rotational virtual knot theory, and there I do not allow you to do the first virtual move, the curl. You can't remove a virtual curl. How could we say this in terms of our detour move? We could say that the detour move is restricted to regular homotopy in the plane or on the two-sphere. You're not allowed to move curls, but you are allowed to do all the rest. So let's go back to the diagram for that, just so you see what the rules look like. For rotational knot theory, you can do everything except VR1. VR1 is forbidden. All the other things are available to you, okay? And sorry, this takes a little time to go forward again. You're getting a fast review. All right, so there's a knot on the left in this slide, and you see, you can't imagine how to undo it if you're not allowed to do the flat curl. And you can't. That's a knot, that thing on the left. And the thing in the middle is a link, and the other one is a link. And it turns out that these are a good domain for studying quantum link invariants. We aren't going to do this theory today in this talk, but I wanted to mention it and show you what it looks like. So you can cancel some curls because I said you're allowed to do regular homotopy of curves in the plane. But some things are definitely irreducible. So you get state circles like the ones at the bottom where there are curls that can't be removed, like these. And then you expand the bracket in the usual way, and you end up with some states with irreducible curling in them that won't go away. And as a result, you can show that some things are knotted. So that's the way this looks. And it's an amusing and interesting theory to think about. Getting back to standard virtual knot theory, what we've said so far is that virtual knot theory is virtual diagrams up to virtual equivalents. It's equivalent to oriented Gauss codes up to Reidemeister moves on the codes that can be described abstractly. And it's the same as links in thickened surfaces up to one-handle stabilization. Now that's a repeat slide. Kuperberg showed something very interesting. He showed that the one-handle surgery gives a unique knot type in the minimal genus surface. That is, you can look for the least genus surface on which the knot would live, allowing it to undergo its Reidemeister moves and everything. There will be some least surface. And that up to topological embedding, that's unique. And so if you knew the least genus surface, then you could forget about all the handle stabilization and just study the knot in that surface. Very nice theorem. Here's the slide I was looking for. This is a good example of a knot that's not in its least genus surface. You can see that by imagining taking the ribbon graph. If you took the ribbon graph, it wouldn't see that handle over there on the left. Even though the knot goes around the handle in one way, it would disappear. And if you look for surgery to remove the handle, well, you can encircle the hole with a curve on which you can do surgery and get rid of the handle. So that's a flavor of non-minimal surface there. Now I come back to the bracket polynomial again, and I remind you, as we had constructed it, that these are our final values, right? That the loop is this, and the curls behave that way. And you see, you can do the bracket polynomial on a surface if you want to. Again, this is just something I'm mentioning, but it's a powerful method if you want to use it. Instead of just doing the bracket polynomial on diagrams, get your knot on a surface. Maybe you can find out that it's the minimal surface, or maybe you use this technique to find out that it's the minimal surface. You expand it in the surface and look at the isotopy classes of the state loops in the surface. It's a technique. I'm not going to go into it now. But this is a nice conjecture. If you have a knot in a surface and it is of minimal genus, then it could well be that the bracket polynomial using it in the surface with isotopy classes for its state loops will detect that. We'd like to know whether this is true or not. Here's another fact about bracket polynomial for virtuals. Just look at this as a little exercise in expanding the bracket. I have two virtuals flanking an ordinary crossing. And I smooth the crossing one way, and I smooth the crossing the other way. When I smooth it one way, the A way, I get a Reidemeister 2 move on the virtuals, so it simplifies. When I smooth it the other way, I get a couple of flat curls, and they simplify. And so I get two standard smoothings that correspond to expanding an ordinary crossing. So the two flanking virtual crossings disappeared, and I found out that if I have a crossing flanked by virtual crossings and I'm calculating the bracket for this virtual knot, I get the same result as if I had smoothed them out, removed them, in that way that you see. And I'll call this equivalence Z equivalence, just for want of a name for it. So Z equivalent knots have the same bracket polynomial. Now let me skip forward on a slide and then come back to this slide. Take the example on the bottom of this slide. If you perform a Z equivalence on the example at the bottom, you get the one on the right, and we know they have the same bracket. But what is the bracket of the one on the right? Oh, that's an unknotted curve, right? There's a big curl which can be contracted by a Reidemeister 2 move to a small curl. So U is unknotted. So that means that the bracket polynomial of the K prime, the knot on the left, is trivial. The normalized bracket polynomial will be equal to 1. The Jones polynomial of K prime is equal to 1. So that's what I said before, that this knot has Jones polynomial equal to 1. But hopefully by the end of this talk, if we have enough time, we will see that this is indeed a non-trivial virtual knot, and not classical either. If it were equivalent to a classical knot, we would all be very excited, because no one has ever found a classical knot with unit Jones polynomial. The conjecture is that there aren't any classical knots with unit Jones polynomial that are knotted. May be true. Let's go back now and look at this again. The construction that I did could be described in the following way. You start with a crossing I on the left, possibly in a classical knot. You decide to draw it almost the same way. If it goes under from top to bottom, it should still go under, but you go down through virtually and then go up under and then down through virtually. So that means that I have reversed the sign of this crossing if we had kept track of orientation. And I have virtualized the crossing in my terminology. I have put those two flanking virtuals in. But we know they have the same Jones polynomial as if I did the Z move. The Z move smooths out the virtual crossings and gives me the diagram on the bottom right. And then I do a little isotopy on the bottom right, and I see, oh, that's the same as having switched the original crossing, flipped it from under to over. So this tells you what we found in another form. It tells you that if you started with a given crossing and you virtualized it, the bracket polynomial would be the same as the bracket polynomial if you had switched it. And indeed, when we looked at this example, you can see that that's what happened. We started with a truffle knot, and the lower crossing got switched in U to form U. So instead of switching it, I virtualize it. Switching it gave me an unknot, and the bracket will be the same as an unknot. But now you see that you can do this with lots of examples. Take any classical knot you like, find some crossings that will switch it to make it into the unknot. You can always do this. And virtualize them instead of switching them. You'll get a virtual knot, and it will have unit Jones polynomial. So you can make many, infinitely many things of this kind. Now, what about triviality and non-triviality? Well, here's a point. There is an invariant called the quandle, and I'm not doing quandle in this talk, but I'm going to imagine that you listening to me know about quandles from some other talks, or maybe before you came to this seminar. In the quandle, you label the edges of the diagram, the arcs in the diagram, by algebra elements, and you label the outgoing line as a product of the ingoing line and the overline. So in this case, A and B and AB. And there is some algebra rules that make such an algebraic structure invariant. Now, we're talking about unoriented diagrams and unoriented quandles. Involutory quandle, it's called, and so I wrote IQ. Now look at what happened when we virtualized. I'm labeling A and B in the same way. I'm assuming that labels do not change at a virtual crossing, so the B runs along all the way over to the left and right, same as it did before. The A runs along, goes through the virtual crossing and is still an A, goes under the B and comes out as an AB and goes up. And you see the external label is still AB, and the diagram does not change its relations at all. In other words, the quandle that you would assign to the diagram on the left is the same as the quandle that you would assign to the diagram on the right. virtualization leaves the quandle alone. Virtualization changes the Jones polynomial, as we saw, from the Jones polynomial of the not with that crossing to the crossing switched. But it doesn't change the quandle. And so that means that we can now be more subtle in our analysis of the trefoil. The trefoil has a non-trivial quandle, as you can verify. And therefore, so does K prime have a non-trivial quandle, the same one. And therefore, K prime is a non-trivial virtual knot. That doesn't prove it's not classical. Might have a zero genus, but it's definitely a non-trivial one. And we have to work harder to prove that its genus is above zero, that it really is a non-trivial virtual that isn't classical. But we have some information here. And that means we're going to be able to produce infinitely many non-trivial knots with unit Jones polynomial in this way. Here's a research question that's still open. Does classical knot theory embed in virtual knot theory modulo Z equivalence? We know that classical knot theory does embed in virtual knot theory. If two classical knots are equivalent using virtual moves, they are equivalent using classical moves. You can prove this by using the fact that the fundamental group and its peripheral system classify the knot, or you can prove it using Kuperberg's results. But if we try this question, we don't know the answer yet. Now here's a conjecture that we had, which we managed to solve. The conjecture is that if you form a classical knot, if you form the virtualization of a classical knot the way we did, then it will always be non-classical, right? That's what I said I wanted to prove for the trefoil case, but I claim that we should know it for every possible case. That was our old conjecture. And it turns out that that conjecture is true by using an extension of Khovanov homology for virtual knots. Now, in the interest of time, I'm going to skip the sketch of the proof of that until we talk about Khovanov homology a little more. That's a sketch of the proof. And I want to talk for the next few minutes. We'll talk until 9:30 and then stop. My 9:30. We'll talk for another 15 minutes or so. I want to talk about parity and a couple of other invariants of virtual knots. Parity is very interesting because it's fundamental to virtual knots, and you get invariance for almost nothing out of it. Here's a friendly virtual knot, not the one we were looking at before. I think we had a picture of this up. This one had Gauss code 1212, as you see. And I note that these crossings are odd. That means that if you look at the 1 and the return, what happens in between before you get to the 1 again, you see only one crossing. And if on the diagram you were to take a walk on the diagram following the arrow, starting at 1, and going around the loop until you get back to 1, you see that you meet the crossing 2 and then you come back to 1. You don't meet two crossings, you meet only one crossing, and you see how that is the case because of the appearance of a virtual crossing in the plane. I say that a crossing is odd if in the Gauss code you see an odd number of classical crossings in between the two appearances of that crossing. So both crossings in this diagram are odd. In a classical knot diagram, all crossings are even. And we can define for virtual diagrams the odd writhe of the virtual diagram, which is going to be simply the sum of the signs of the odd crossings. So in this case, the odd writhe is -2. There are two crossings, each one has sign -2. So we have the parity slide, okay? And you followed this, yes. I was talking about this slide. Okay, good. So I define the odd-rive to be the sum of the signs of the odd crossing. And here's an exercise for you. Try it for the next time and we can talk about it. That's invariant under virtual moves, okay? Not hard to see that summing on just the odd crossings is invariant under the virtual moves. All of them, not including the first virtual move, the curl, including the ordinary classical curl. Classical curls are not counted by odd-rive because in a classical curl, you go from the crossing right back to it, and it's even. So it's an invariant of virtual isotopy. It's zero on classical knots, and under mirror images, it changes sign. So among other things, knowing that, we've proved that this knot here is inequivalent to its mirror image. Very easy. So parity is a good thing. And there is a very beautiful idea for getting more information about parity that's due to Vasily Manturov. And here's his prescription. You take your diagram, and for every odd crossing in the diagram, you turn it into a graphical node. And for every even, and now you have a new diagram with graphical nodes. And now you expand that diagram on the even crossings by the bracket. And of course, you will get some graphs. And you must reduce these graphs by doing Reidemeister 2 moves whenever possible on the graphical nodes. Just reduce. So a graph is to be reduced when you see two nodes in Reidemeister 2 configuration. And then you take the resulting combination of graphs times polynomials, and that will be invariant under the moves. Nice exercise to check that. And some knots are very quickly detected by using the parity bracket. For example, here is the Kashino knot. The Kashino knot is easily seen to have Jones polynomial equal to 1, but other invariants also vanish, such as the quandle and the fundamental group. And so it's a nice test case to see how to detect it. And in this case, why all you have to do is notice that all the crossings are odd, and they are if you count. And so they all get nodes. And then you look at this graph and you realize that there aren't any reducing 2 moves. And so that's it. That graph on the right of the diagram is the parity bracket of the Kashino knot. So that means that this graph must occur in every diagram you ever make of the Kashino knot, up to doing smoothings like the bracket does. This is a theorem about the appearance of graphs in knots that is a little like finding minors in graphs, if you're familiar with minors in graph theory. In any case, we've proved that Kashino is non-trivial. And we can do it for other examples as well. For example, here, if I look at the Gauss diagram for this knot that I have drawn over here, I see that every crossing is odd. And so that means that I have detected this one as well. And you can do other examples as well. I'm going to skip these examples in this case, just so we can go on a little bit to show you another invariant. I want to talk about one more invariant today, and then we'll stop. And this invariant is the arrow polynomial, which is due to myself and Heather Dye and to Naoko Kamada and Miyazawa independently. And the arrow polynomial generalizes the Jones polynomial by thinking along the following lines. Suppose you're expanding the bracket, but you decide to put in the orientations. Then you would expand and get an ordinary smoothing, and you would get a disoriented smoothing where 2 arrows went to a point and 2 arrows emanated from a point. And you could wonder whether you could use that strange combinatorics of arrow cusps, because this tells you how to calculate the bracket all right, But the way you would usually calculate the bracket would be to ignore the cusps. What if we didn't ignore them? What if we tried to use them? Could we keep some cusp structure in the process? Well, it turns out that this is the answer, an answer to that question. We'll think of the cusps as independent of one another. They aren't paired at the crossing anymore. And then if you have two cusps that occur on the same side of a line, they can cancel. But if they occur on opposite sides of an arc, they don't have to cancel. That means that when you get down to the states, you get states that have non-trivial zigzagging cusp structures like the ones I've drawn at the bottom of the slide. And those are allowed to be different. You just reduce the states by consecutive cusps on the same side of an arc cancel. And then it will be invariant under the Reidemeister moves. And we get new variables, one for each zigzagging loop. So we have suddenly infinitely many variables. And this is going to mean a lot for virtual diagrams, and it doesn't happen in classical diagrams at all. There will be no zigzagging states from a classical diagram. How do you get an idea of what's going on with this, and how do you see that it's invariant? We have enough time to get a little bit of an idea. First of all, the zigzagging can happen if you're on a surface of higher genus. Here's a state drawn on the surface of a torus. And as you see, the loop, the meridional loop, has zigzagging in it, and it is matched by another loop which goes all the way around from one side of that loop to the other. When you have the Jordan curve theorem acting, and every loop divides the space into two pieces, this won't happen. And as a result, the zigzagging can't actually occur in the plane, but it can occur in higher genus. Now, what about invariance? Well, I wanted to show you the proof. So let's look at what happens when we expand the bracket and keep track of the cusps. So here's the Reidemeister 2 expansion for going in oriented way parallel. And you see we get a cuspy, I'm going to do it this way so I can point. We get a cuspy loop here. Yeah? And we get a couple of pairs of cusps here and a pair of cusps here and an ordinary smoothing there. So in order to collect terms the way we did before to get a cancellation, we need that the cuspy loop should be evaluated the same way as an ordinary loop. And in order to do that, but our rule tells us that we can do that because these two cusps occur on the same side of that curve, so they cancel. And they are the same as an ordinary loop. Okay, so our rule tells us that we'll get invariance here. What about this one where the orientations go in the opposite direction? Then the loop that comes out is oriented, but we get some interesting cuspy stuff here and here. But again, this cusp occurs on the same side as this cusp, and they cancel. And so this is an ordinary curve, and this is an ordinary curve, and these three bits collect up together and cancel out as they did before. So this is good. We get invariance under the second Reidemeister move. And now, what about the third Reidemeister move? For that, we have to watch carefully, and you'll see what happens with zigzags. I have the following lemma, that if I have an arc that goes underneath a cusp, you can pull it up out, but it acquires a zigzag. And if it goes underneath the cusp the other way, with an opposite orientation on the cusp, it acquires an opposite zigzag. The proof is easy. Here you expand it, and you expand it again, and you look at in the expansion, and you see that you get some zigzags in the expansion, and other things that cancel out. So it's a little calculation, and you get this lemma of the production of zigzags by doing Reidemeister 2 moves on cusps. And now we do the 3 move. Very similar to the old argument. You see, Here I am, and I'm underneath, and I expand this. Now I have an undercrossing of a cusp, and this one's normal. The undercrossing of the cusp can be pulled out by our lemma and produces a zigzag, but that zigzag can be absorbed by the upper cusp by the same lemma, and now it's up where it belongs, where we want it, and we see that we have the expansion, and we got the invariance under the third move. So zigzags are good, and we don't have to throw them away. We can actually even use them. And so we have the invariance of the arrow polynomial. And then we can use the arrow polynomial to do lots of detections. And I'm going to skip this slide and show you a standard one. We want to show that this guy here, for example, is non-trivial. So you look at the states of him, and you see that some of the states, this one, and this one, have a zigzagging situation and give you a K1 variable. And that proves that this is non-trivial. But we already knew it was non-trivial. Similarly, you can prove the Kashino is non-trivial. But there's more about this invariant. For example, you can ask, what about the number of virtual crossings in the diagram? And it turns out that a lower bound for the number of virtual crossings in the diagram is the k degree. In this case, the highest degree that the k's can produce is 2. The k degree in general is the degree of the ki, like you might have a k2, and that would be of degree 2, and then you look at its powers. So the k degree gives a lower bound on the virtual crossing number. It's interesting to see how these funny cuspy zigzagging things occur when you expand somebody. The Kashino is detected by the arrow polynomial. We already proved it was detected by the parity bracket, but this is a separate method. And we could now go to another polynomial invariant, but I think it's time to stop. So what we're going to do next time is begin here with the index polynomial. I'm willing to talk about any questions you might have on what we had done so far. After the talk, I will send this slideshow over so that you can get hold of it. And we will continue next time talking about the index polynomial and then about Cobordism of virtual knots and a bit about Khovanov homology. Thank you very much for listening.
Thank you, Professor Kauffman. So any questions from participant students? There's one question. Virtual crossing is ignored while computing bracket polynomial. Can we enhance this polynomial by adding data to the virtual crossing link for classical crossing to prove non-triviality of few virtual knots with the unit polynomial? That is one question from Nehananda.
In some algebraic cases, you can indeed add extra information to the virtual crossing to get more information about the knot. I indicated in the slideshow a way to enhance the bracket polynomial. I actually indicated 2 ways. They are not using a strategy of doing something different at the virtual crossing. Those ways were, and let me remind you what they were. One way is to take the virtual knot on a surface and then look at the isotopy classes of the state curves on that surface. And then you get an invariant of the knot in that surface, but you can often tell whether that knot surface is minimal, and you can tell a lot about it. And you could, if you add some extra bells and whistles to the equivalence relation, regard the isotopy class of state loops on the surface kind of invariant as an invariant of virtuals fully. So that's one way to enhance the bracket. Another way to enhance the bracket is to take into account parity with the parity bracket polynomial. And there I am using information about the virtual crossings, the parity information, to get a version of the bracket that can give me information that is new. And then the last thing that I did was the arrow polynomial, where I didn't add information about virtual crossings. I added orientation information about classical crossings in relation to the virtual crossings, and that's what gave rise to the zigzagging states. So in an indirect way, I am using the virtual crossings to enhance the bracket polynomial in a number of ways. And finally, you could take the arrow polynomial that we just defined and look at it on the surface, if you have the knot on the surface, and take the isotopy classes of the states of the arrow polynomial, and that gives you an even stronger invariant. The question of how you might directly do something to the virtual crossing to extend the bracket is an interesting question. I haven't a good idea about how to do that directly. You might think about it. Maybe by the next talk we can invent something. The next question was, is it right that a virtual knot is a classical knot in which we decide that some crossings are virtual? Well, yes. In the sense of diagrams, that's correct. You could draw any classical diagram you like and then make some crossings virtual. The next part of the question is, if we consider a surface and then knots in 3 space f cross I, what is the relationship between virtual knots and the linear skein space? That's not obvious. The virtual knot theory is ignoring and embedding into 3 space of f cross I. So you get quite different results. For example, a torus knot, as is usually considered, is a trivial virtual knot. It doesn't have any crossings on the surface of the torus, but it's non-trivially embedded in the torus cross I in 3 space. So so I think it's an interesting question, but it isn't one that I know a good answer to. Could you please come back to the virtualization operation that preserves the quandle but changes the Jones polynomial? You mean you'd like me to talk more about it? I will next time. Think about what you're asking, and next time we can talk about it a little more. And is the knot theory an aspect of graphical models? What do you mean by graphical models? What is a graphical model? Whoever asked the question, Christopher, yeah? What is a graphical model for you? Can you answer my question? I don't know the meaning of the term graphical model.
Maybe he might be talking about the spatial.
All right, thank you, Prof. Thank you, Prof. Yeah, graphical models are representations of a model in terms of lines and spaces. Instead of writing the equation, you can represent it using some charts, some graphs, and conduct some inference on them. So I'm coming from the angle of representing an equation or a model in terms of a graph, like directed graphs.
Well, let me try this. I mean, I think when you say graphical models, you mean using graph theory to model other subjects, right?
Yeah.
Like graph theory models transportation problems by taking just the connection structure that is available between a collection of points and evaluates operations research questions on the graph, right? Here, Here indeed, we are making a graphical model of the embeddings of knots in three-dimensional space by using the diagrams. And
Okay.
so you can think of this as a graph theoretic approach to knot theory,
Okay.
except that
Okay.
it was always more held by topologists as a diagrammatic topological approach, because most graph theory models do not concern themselves with collections of moves on the graphs. And we
Okay.
have in the knot theory some very special moves and the equivalence relation that's generated by those moves. I
Okay.
imagine that in the future, the subject of graphs and graphical models will include lots of situations where there are graphs and there are certain moves on those graphs that have to be understood.
Okay. Thank you, Prof.
This question says, there's a way to describe bracket polynomial as arising from a theory of Feynman diagrams, and the horizontal and vertical smoothings are interpreted as annihilation. And does this? Yes, it does. Yes, it does. I call that quantum link invariance. And as long as you ask the question, let me remind myself to talk about it a little bit next time, rather than start lecturing you about it now.
There is one more question regarding, can the polynomial invariants for virtual knots also arise as quantum invariants?
This question says, while forming the ribbon neighborhood, how did you make the choice of which strand should go over at the virtual crossing? You will remember that I drew it so that one ribbon went over the other. And I said, and you didn't hear me maybe. It's easy not to hear me because the diagram is so strong visually. I said, I don't care whether it goes over or under. I don't care, because the surface that I'm making is an abstract surface, but unfortunately, in order to draw it and communicate it to you, I have to draw it one way or another. So in that case, it didn't matter. I didn't have to make a choice. The choice was strictly artistic. Other questions?
Okay, it seems there are no other questions. Thanks a lot, Professor Kauffman.